and welcome to CO 738 Probabilistic Methods. Today we'll be discussing Jansons Inequality. So what is Jansons? Here's the motivation. Suppose we want to upper bound the probability that none of a set of events, bi in some index set I, occurs. Now, if the events were actually mutually independent, then the probability that none of these events occur would of course just be the product of the probability that each individual event did not occur. So it'd be the product of little I and big I of the probability that bi did not happen. But the question we're asking today is, what if the events are just mostly independent? So what if they're mostly independent? Then the answer that we'll be looking at is the Janson inequalities, there's multiple, allow us to sometimes say these are nearly equal. So it's the actual probability get is close to being what it would be as if they were mutually independent. So this is quite helpful when we want to upper bound these probabilities, which should be reminiscent of things like the low-Voss local lemma. There, though, we're trying to say that the probability none of the bounded ends occur is actually greater than 0, which is a lower bound. Here we want an upper bound. That might be similar to concentration inequalities, but those don't always work in this desired way, because the idea is we want to get them to be exponentially small. So given these tangential relations to the other things we've done, Jansons fits a nice niche that we haven't really explored before of how to actually accomplish this. But we need to discuss its setup. So what is the setup? So Jansons will work only on a specific setup. Here is that setup. The probability space will let omega be a finite universal set. And the idea is we're looking at the probability space where R is a random subset of omega, where the randomness is choosing each R and omega independently with a probability PR, P subscript little r. So each element can have a different probability. So this is somewhat like GNP, but again, each element could actually have a different probability of being chosen. So that's quite a general setup. And then we'll be looking at events. And we'll let AI be subsets of omega. So these are sets of elements that we want to be chosen, and I some, again, finite index set, so the finite number of events. Then for every I in the index set, we'll let bi be the event that AI is a subset of R, that AI has been chosen. So the bi will be these, we have a family of subsets, and each event will be whether that subset is all been chosen. And the question is, what about this probability of that none of those happen? Well, to do that, we're going to need to talk about dependence, because again, these may not be independent if they overlap in elements. So the notion of dependence here, a la the variable model, is that for every ij in the index set, we say that I, twiddle or tilde j, if I is not equal to j, and ai intersect aj is not equal to the empty set. So that makes sense. Then they would overlap. They would be dependent in a way. And we'll note that bi is mutually independent of the other bj's for all the j's that it's not this twiddle, this tilde for. So it'd be mutually independent of anything it doesn't overlap with. And we're going to define a dependency measure given that, which we'll denote as delta, and this should be reminiscent from the second moment model method, that we'll take the sum over I tilde j of the probability that bi intersect bj. So this will be our key notion that we're going to use to discuss what it means to be nearly independent, is we're going to sum up all these, the product, somehow we're going to sum up the probability that bi and bj both happen for all the ij's that are actually dependent. So all these pairs. So somehow this probability then will detect somehow pairwise this overlap, which is similar to the covariances if you think about it from the second moment method. So given that setup, again, what is we doing? Our target bound we'll define as m, which will be the product for I in I of the probability that bi does not happen. So it's the thing we were interested in bounding. That's our target bound actually. So we're interested in the probability of the intersection of these. So this would equal the probability of the intersection if the bi's are mutually independent, but they may not be, and so this is our target bound of what we'd like to achieve. And then the underlying variable that is of interest, so we won't necessarily use, but I'll just make a note of it, is the number of chosen events. So really you should think that each set is somehow an event, and we want to count how many events happen. So for every I in I, we let xi be the indicator random variable for bi. That means it's a 1 if bi happens, that is all of the elements of ai are chosen, and a 0 otherwise. And we'll let x be the sum of these. So x will count the number of subsets we ended up capturing with our random set. And we know that x is 0 if and only if none of the subsets are captured, so none of the bi happen. And then the expected number of events we can define as mu to be the expectation of x, which would be, of course, the sum of the probabilities of the bi. So that's the expected number of subsets to capture. And that'll be important for the actual statement of the inequality. So once again, we have this target bound, we have an expected number of events, and we have this dependency measure delta. So now we can state Jansons inequality from 1990. It says if we let these bi be the setup in the same probability space and all that, and we have delta as we had defined, and we have m our target bound, and mu this expected number of events, all as defined before. And I'm going to add an additional assumption. If the probability of the bi is all at most epsilon, for some fixed epsilon there, for all I, so that's saying the probability that we actually select any of these sets, each one is individually small, then what we can find is that m, the target bound, is actually a lower bound for the probability that none of these events happen, which is also upper bounded by m times a bit of a fudge factor. So it's e 1 over 1 minus epsilon, it's the ceiling there, delta over 2. So if you think epsilon's, a half or a tenth, I mean, that front number is really close to 1, and so it's just kind of a constant. Really, the thing there is delta over 2. So somehow if that pairwise dependency measure, that delta is small, this says that these really are rather close to equal. And then furthermore, we can do a bit better, or different rather. We can also get a different upper bound, which is that the probability is at most e to the minus mu plus delta over 2, which would be more reminiscent of the things coming from concentration inequalities, that you'd kind of hope to get a e to the minus mu, but you'd have to maybe give up a bit. So let's discuss that. What is the difference between these two upper bounds? We'll note that for every I in I, the probability that bi doesn't happen, which is 1 minus the probability bi does happen, is, by the standard inequality, at most e to the minus probability of bi. And so if you multiply that over the I in I, which would give you m, then you'd actually get an upper bound for each, which would sum up in the exponent, so that would give you that m is at most e to the minus mu. So that second upper bound, the e to the minus u term, is actually an upper bound of m, and so they are rather close. There's the first bound has this 1 over 1 minus epsilon factor that the second doesn't, so they're slightly incomparable, but really they're quite similar, and the second tends to be more convenient to use in practice, since it may be a bit hard to actually write down this product to find this m. And so then you just use the e to the minus mu, may be a bit easier. So that's Jansons inequality. When we have this setup of this probability space, and we have these bi being the events that they're sets ai where all the elements were chosen, then we can actually get pretty tight concentration away. We can get a pretty tight understanding of what this probability of the bi is. All right, so that's Jansons. I will mention that the above bounds are useless if delta is at least 2 mu. So if the dependence is a bit too much, if you go back to those, you'll note that in the second equality, then you don't really get anything, and the same in the first. So what do we do in this case? Well, it can be improved using the following. So there's actually a trick to get an extended version of Jansons, which works in this regime, which goes as follows. If in addition to all the above, we assume that delta was actually at least mu, so we know that we're in this kind of larger regime, then we can instead use the inequality that the probability that all these bi don't happen is at most e to the minus mu squared over 2 delta. So instead of just getting kind of like a mu plus a delta, so this may be useful, right, if delta is at least 2 mu, but maybe still smaller than mu squared. So if delta is smaller than mu squared, this will actually be a rather useful. So in a somewhat larger regime, we can use this other inequality. And why should this seem a bit reminiscent? Well, it's somewhat related to Chebyshev's. So But basically this gives a much better bound than Chebyshev's here. How so? Well, from before, in this kind of setup, the delta was these covariances. So before we were able to show that in that case, the variance of x was at most mu plus delta. And then Chebyshev's would give you that the probability that one of these events happens, which is the probability that x, the number of events, is 0, is at most by Chebyshev's the variance over the expectation squared. And then what does that give you? That's at most from above mu plus delta over mu squared. And so the point is, if we're in this regime where delta is a bit bigger than mu, Chebyshev's would just give you something like delta over mu squared. This would give you, extending Jansons give you e to the minus kind of mu squared over delta. And so is a bit better then. So that's the idea that Chebyshev's, while useful in the case where delta is smaller than mu squared, may only kind of give this linear factor. And here we get an actually exponential decrease using extended Jansons if we fit this better, more specific model of the probability space. All right, so those are the inequalities. In the remainder of our time today, we will go ahead with proofs. We're going to prove Jansons, we have to prove a lower bound, we have to prove 2 upper bounds, and then extended Jansons. So that's a lot of work. And the proof we'll do today will follow the proof of Boponda and Spencer from 1989. So Janson's original proof used Laplace transforms. Here we'll use an approach that is closer to the proof we did of the Lovász local lemma, using that somehow more compares it to how they're independent. And to do this, to ease up the notation a bit, for S a subset of I, we'll write naught S. I won't use this all the time, but when it gets a bit crowded, to mean the naught of all the events I and S, so the naught of all those BI. And then here's somewhat the key proposition we're going to need, which is under the assumptions of Jansons, for every j, a subset of I, and ik not in j, you get 2 nice inequalities. One is that the probability of bi, given not j happening, is at most the probability of bi. And the second one is similar. It's the probability of the bi conditioned on bk and not j is at most the probability of bi just conditioned on bk. So somehow, when there's somewhat of a not j that we're conditioning on, we can kind of get rid of that in an upper bound style. So how is this proof going to go? This is where we're going to use those correlation inequalities, FKG, Clavenslemma for function theorem style that we did before. So let's go through that. So for the first one, the property bi, we can view again this as a lattice, right? So we're choosing the different elements. So that's the lattice 2 to the omega, and the property bi is indeed increasing on that. If we've already chosen all of ai, then any larger set will also contain ai. And similarly, the property of not j is decreasing, right? If we turn some of the elements off, it can only make us more not j. So given that, we can apply the generalized Clavenslemma, right? So Clavenslemma is when we chose each element with probability half. We generalized that to where each element was allowed to have a different probability. We only applied it to G and P where they each had the same probability that wasn't half, but it actually held even more generally when they each have a different probability as in this setup. And again, that followed from the FKG inequality, which followed from the 4 functions theorem. So given that, so BI is increasing and not J is decreasing, our lemma said that the probability of this, they're anti-correlated so that they'll end up having the probability will must be the product of the probabilities of BI and probability of not J. And then if you just divide the above equation by not J, you get the left-hand side is probability of BI conditional not J, the other right-hand side is probability of BI. That's the inequality, the desired inequality of this proposition. And it's rather similar for the other one. And there's even a trick you can do to say it's really identical, is for the second equality, conditioning on BK is really the same as choosing all the elements of AK, right? So it's making sure they're all on. And then what does that mean? We can really think that we're restricted to a sublattice, right? L prime, I'll call it, where A, if you have the sets will be A as a subset of omega, where AK is inside of A. So we're conditioning on BK means that we're only interested in supersets of AK and we get this new sublattice. But again, bi intersect L prime is increasing in L prime. So any such set, then actually any of its supersets also satisfy the property. So again, it's increasing, and similarly not j intersect L prime would be decreasing in that sublattice. And so then when we apply the FKG, this generalized Kleitmans, to that sublattice, we'd actually get the same inequality. We divide through, and we find that the second inequality also follows. So that concludes the proof of that proposition, which I haven't told you yet how we're going to use it, but somehow because of these correlation inequalities, there are nice things we can do probabilistically, bounding these conditional probabilities. So now back to the main proof. Well, the lower bound is actually rather easy, so you could do it from first principles, but here, since bi is decreasing, we have, by repeated applications of that generalized Kleitmans, that m, which is the product of the probabilities, is strictly smaller than the probability that none of them happen, right? So since they're all decreasing, they're all correlated, and so the probability that they all happen would be strictly greater than their product. So that's maybe the easier way to do it given Kleitmans. For the upper bound, that's going to be a bit harder. We're going to need that proposition. We're going to order the events b1 up to bn, so we're just going to give them numbers. And now, here's the key claim, is that for every I in n, the probability of bi, given not bj, where those are smaller, is at least the probability of bi minus this dependency sum, minus the probability of bi intersect bj, where we sum over j that are smaller than I, of I that are dependent with j, so whose sets overlap. So why are we doing it only for j that are smaller? Again, like in the Lovász-Lóka lemma, to upper bound that probability, we can take a product where we condition an event on the previous ones. So we only have to really look to the smaller. And so that's what we're going to do. All right, so now that we have that, we have to prove this claim. So how do we prove that bi conditioned on these smaller ones is not happening is not too bad, right? So we know from the correlation inequality that the proposition, when we condition, we know it's at most the probability of bi. This is saying that it's at least the probability of bi minus this little fudge factor coming from those pairwise dependencies. So then this is the key claim, really. How do we do this? And then the rest will follow. We'll go through that, but let's prove the claim. So we fix a specific I, it doesn't matter, so just pick one I. And now I'm going to break up everything smaller, which is 1 up to I minus 1, into two sets. D, which will be the ones it's dependent on, and R, the ones that it's independent of, the remainder. So we have this D and we have this R, and now I'm going to define 3 events. So I'm just going to rename to make it easier so we don't have to carry around everything. We're going to let A be BI. So I know that's terrible, but just go with me. We're going to let B, the second event we're carried, is not D. So what if none of the dependent events happen? And C will be not R. So none of the remaining events happen. So given that, what are we interested in? So we're interested in BI given that none of the smaller things happen, which is A given that neither B nor C happen. So B and C not happening, right? So we need that, which we can of course rewrite, if you remember what conditional probabilities are, as the probability of A intersect B intersect C divided by the probability of B intersect C. So what good is this? Well, we can then do a bit of arithmetic manipulation here, some probabilistic manipulation, to rewrite this in a better way. So let's go through that. First, I'll note that the probability of B intersect C is at most the probability of C. So I can actually write that this is greater than or equal probability of A intersect B intersect C, so the same thing up top, but replace that bottom with the probability of C. And why should that be nice? Well, you can think that that's actually, if I rewrite in conditional terms, that's the probability of A intersect B given C. So that's just an inequality that holds for all A, B, and C in a probability space. It has nothing to do with the setup for Jansons or anything. So that's the first step. Now I'll use a trick where I'm going to do both a numerator and denominator of the probability of A intersects C. So I'm going to break it up so I have probability of A intersects C divided by probability of C times probability of A intersect B intersect C divided by the probability of A intersects C. And why is that good? Well, then we can rewrite those both as conditionals. So namely, we have the probability of A given C times the probability of B given A intersects C. So it's a bit strange, but indeed this shows that the probability of A given B intersects C is at least the probability of A given C times the probability of B given A intersects C. So we've managed to switch B from the given to what we're looking at. And now we just have to investigate these two terms to prove the claim. So the first term is easy. Since A and C are independent, right? So A is BI and C is not R. So they're the remainder, so we're interested in not the remainder, but those are the ones that BI did not depend on, didn't overlap with at all. So A and C are truly independent events, so the probability of A given C is just the probability of A. So that makes our life easier. So this main, remember, this is what we're trying to lower bound, this probability A given B intersects C. That first term is just the probability of A, so we have to study that second term. Probability of B, which is not D, given A, which is BI, intersect C, which is not R. So now I do some manipulation. I'm going to take the complement and use the union bound. So how does this work? Well, the probability of B given A intersects C, that's 1 minus the probability of not B. But what is not B? Not B was not D, so not cancels. So it's really do any of, the complement will end up being, do any of these BJ end up happening, right? So none of them at all happened. So the complement will be, does one of them happen, right? So we have that, and now that's where you can apply the union bound, right? So the union bound tells us that negative term there, the inner term is smaller than the sum of those probabilities. So this would actually be greater than or equal to 1 minus the sum of J and D of the probability of BJ given A intersects C. Okay, so what good is that? Well, this is where that proposition comes in. So what are we looking at? We have probability of BJ given A, which is BI, and intersect C, which is not R, so not any of the things I is dependent on. And what we said in the proposition is any of these nots that are in the conditional, we can just move out. We can just get rid of entirely. So we just get that this is equal to the probability of BJ given BI. And then we get that hence the probability of BI given none of the BJ is always at least this probability of the BI, so that would be the first term. So remember we had this inequality from before where we had probability A, that's probability BI, and then above we had this 1 minus the sum of the probabilities of the BJ given the BI. And what good is that? Well, the first term, the probability of BI is what we wanted. The minus, though, the probability of BI times the probability of BJ given BI is just the probability of BI intersect BJ. So that'll be that sum, that pairwise sum we wanted. So that concludes the proof of the claim. Now we're going to use the claim. So how do we use the claim? So we have to do two upper bounds and then the extended one. But now they really follow just a bit of arithmetic. So let PI be the probability of BI, of not BI, given none of the smaller ones. So that's the opposite of what we had in the claim. So if we multiply the previous claim by -1 and add a 1 to both sides, we'll get the PI as we want. The inequality become reversed, so it'll be less than or equal. And then instead of probability of BI, we'll actually have a 1 minus there, so we can group that as probability of not BI. And then instead of minusing the sum, we'll have a plus of the sum. So we'll have a plus of these sum of these BI intersect BJs. So that's what you get for each PI. And we're interested really in the product of the PIs. So we'll do a slight trick here. Since the probability of BI, not BI, is always at least 1 minus epsilon. And this is where we're using that fact that each PI had probability at most epsilon. We have that PI is at most probability of not BI. We're going to bring that term out now and write then the rest as 1 plus 1 over 1 minus epsilon of this sum of these probabilities. So that's a nice trick, is the probability of not BI isn't really much, so we can just kind of at an expense of a 1 minus epsilon factor, make sure we fold it in instead of an additive factor as a multiplicative one. Then we'll use the fact that we can always upper bound 1 plus x by e to the x. So we'll actually write that second term upper bounded with e to the 1 over 1 minus epsilon of the sum of these pairwise probabilities. And now we're essentially done with the first bound because we were interested in the probability none of them happen. which is the product of these PIs, so using the telescoping conditioning. And then that would be what? From above, we could upper bound each one by the probability of the BI, so all those would products, that would give you M. And then we get the product of these exponential terms, which we would then sum in their exponents, and then we get e to the 1 over 1 minus epsilon ceiling, delta over 2. Since each pair, ij, appears once, not twice here, right? So when we sum them up, we're only get a pair when j is smaller than I. I didn't really stress that, but when I defined it, we mean for all the pairs. So each pair gets counted twice because it's ordered pairs. So you actually get delta over 2. So that just depends on how you define the delta, but we would get that. So that concludes the first bound. As for the second upper bound, it's pretty much the same. We just start from a slightly different place. So we said that pi was at most the probability of not bi plus those sums. Well, let's go back, undo that. Let's say it's replace the probability of not bi with 1 minus the probability of bi, and then use the exponent on that term. So we use 1 plus x at most e to the x to get that this is at most, pi is at most e to the minus probability of bi there. So that should be, sorry, that's a typo, that should be probability of bi, plus the sum of the bi intersect bj's. And then if you do that all together, you product them again, you will get that that's at most, these e's will all product. If you sum up the probability of the bi's, that's mu, so you get minus mu there. And the other terms again gives delta over 2, since each pair appears again once, not twice. So that concludes the proof of the second upper bound. As for the proof of extended Jansons, this is where it gets interesting. So the second upper bound can be rewritten as, if you just take kind of the negative log of both sides, you get negative log of the probability of none of the bi. That again, the inequality reverse because you have negative, so at least mu minus delta over 2. What good is that? Well, actually, if you think about it, we can apply that inequality not only to I, but to every subset of I. So every subset S of I, if you apply it only to the bi's in there and just throw out those extra events and don't care, you would find that the negative natural log of the probability of none of the bi's in S happening is at least the kind of the mu for S and the delta for S. So what is that? The mu for S is the sum of I and S, the probability of bi. That's the expected number of events in S to be chosen. And the delta thing, you'd only take pairs that actually both live in S. So it'd be minus 1/2 the sum I and j, both in S and I dependent on j, probability bi intersect bj. So that's really the cool part. We can, for every subset, we'd actually get an inequality as well. So what good is that? Now we'll use randomness. So we'll let S be a random subset of I, where each element is chosen independently with probability p to be determined later. So we're going to use the probabilistic method to prove a probability theorem. So this is delightful, right? So that's the idea, is that we'll use this randomness and we'll try to conclude that there is actually a decent choice of set S to apply this to, that will then allow us to do this extended Jansons. So let's proceed with that. So by linearity of expectation, since we know that above inequality works, then if we take expectations, we know the expectation of that negative log is at least the expectation on the right side, which by linearity is the expectation of the sum of these probability of bi minus half the expectation of these pairwise sums. So what good is that? Well, each probability of bi term appears with probability p, right? So there's only a p chance that that individual term is chosen. As for the pair term, you need both of them to be chosen, so that happens with probability p squared. And so you can therefore work out that that right-hand side is actually equal to p mu minus p squared delta over 2. So then we have this bound that the expectation of this negative log is at least p mu minus p squared delta over 2. And just as before with things like Chernoff and Hofstein's, now we want to optimize. So we set p to be the optimal. So if you work it out, the optimal choice is mu over delta. And here, crucially, this p is at most 1 by the additional assumption, since delta was at least mu. So why do we need that? You might want to stop and pause and think for a moment. It's because it's a probability, right? We actually do this random experiment. We need p to actually be at most 1. Now it needs to be a real probability, non-negative and at most 1. and indeed it is by the additional assumption. So this really will work. So that's an important thing to remember when you're setting up probabilistic spaces. You need, the choice to choose an element there to be most 1. So now that we've done that, we can plug it in, and well, if p is mu over delta, then you get mu squared over delta, but you get a minus mu squared over 2 delta, so that cancels to give you that you're at least mu squared over 2 delta. Now we're almost done. So we know in expectation of this random experiment, this negative log is pretty good. It's this mu squared over 2 delta, just like we wanted in the inequality. So that means that there exists an S, I don't know what it is, but there exists some subset that gets this expectation. So that minus log is actually at least mu squared over 2 delta. And then, what does that mean? If we take this minus log, if we raise it with the exponential, the negative, then we get that the probability that none of these bi and s happen is at most e to the minus mu squared over 2 delta. And that's the term we wanted from our inequality. And now we're done because, well, what's the probability that none of the bi happen? Certainly that's at most, for all I, that's certainly at most the probability that none of a subset happens. And so the desired inequality would now follow. So this was a nice extra proof there where we used this clever idea that we could choose a subset to apply it and calculate the expectation. So we could use the probabilistic method to prove a probability theorem. That was for extended Jansons. For Jansons, we essentially just used the correlation inequalities to derive, with some arithmetic there, the upper bounds for Janson and the lower bound as well. So today we studied Jansons inequality, which gave us a setup very applicable to when you want to show that the probability none of a set of events happens is actually close to what it would be if they were independent, as long as under the assumptions that they're somehow mostly independent, this delta, this sum of these pairwise probabilities. So that's all for today. Until next time, see you then!